Good evening. I hope all the participants have joined. Please join fast. Our expert is also available. He will start the session within 2 minutes. So please join. Uh, okay. So good evening, and I, Dr. Pooja Shah, again welcome you all on the second day of AICT sponsored faculty development program of Smart Health AI. Uh, Hello, every audible? Okay. Smart Health AI, that is a healthcare solution for the modern healthcare systems. On this second day, I again welcome you all the participants. We are delighted to have you back, and we continue our journey for exploring the transformative role of AI in modern healthcare systems. Today, we will deep dive into these innovative solutions, real world application, and the latest research shaping the future of smart healthcare systems. Your active participation and engagement on the first day, that was a strong foundation, and we took forward for the building on that momentum with the insightful sessions, interactive discussion, and knowledge sharing. So let's continue to learn the collaborative, innovative together towards the smart and healthier tomorrow. Okay. On the second day, I am giving the briefing about our first session expert. He is Dr. Maitrik Shah. He has received his BE in Computer Engineering from the LD College of Engineering and MTech in Computer Science and Engineering from Nirma University 2012. He was honored with the gold medal for the best academic performance and recognized as the best student. He is currently serving as an assistant professor in the Department of Computer Engineering at LD Engineering College, Ahmedabad, a position he has held in since 2016. Prior to this, he was associated with the Indus University from 2012 to 2016. With over 12 years of teaching experience, Dr. Maitrik Shah has mentored, motivated, and guided more than 1,000 students throughout his academic career. He has earned his PhD from the School of Engineering and Applied Science at Ahmedabad University. His research focused on the remote sensing and satellite image analysis with a specialization in atmospheric correction. His work explored the use of deep learning as a data-driven alternative to the traditional physics-based atmospheric correction models. Dr. Shah is a member of IEEE Geoscience and Remote Sensing Society. He has received the Best Paper Award at IEEE in GA-RSS 2022 and was awarded IEEE GRSS Travel Grant for the presenting his research at IEEE IJA-RSS 2022 Malaysia. Australia, and notably, he was selected as one of the top 10 finalists in the 3-minute thesis completion at IEEE IJA-RSS 2022 held in Kuala Lumpur, Malaysia. So without wasting time, I welcome Dr. Maitrik Shah to start the session. Sir, Maitrik sir.
Thank you very much, Pooja ma'am, for the nice introduction. I hope I'm clearly audible.
Yes, sir. Okay, thank you.
So, shall I share my screen?
Yes, sir. You may share now.
I hope my screen is visible.
Yes, sir. Your screen is visible.
Thank you. So, I'm very thankful to the organizers for inviting me for this Atal Online FDP on Smart Health AI Solutions for Modern Healthcare Systems, which has been organized by Vidush Somany Institute of Technology and Research, Kadi. I really feel privileged to give an expert session on predictive analytics. So basically, I have changed the name of AI from artificial intelligence because in my presentation, I have two different components. One is analytics and intelligence. So predictive analytics intelligence in healthcare. Uh, I really feel privileged to give this session to these August participants. So this is the outline of my presentation. We'll start with an overview of predictive analytics in healthcare by examining how it uses historical and real-time data to forecast disease risks, support clinical decisions, and optimize resource like the readmission prevention and population health management. Next, we'll understand the challenges in traditional healthcare systems and how AI is stepping in to overcome them. Then we'll dwell into deep learning use cases, including breakthroughs in medical imaging, the state-of-the-art research which has been done in the literature for using deep learning for identifying the lung cancer, the diabetic retinopathy, and skin cancer, which has achieved near human accuracy. Following that, we'll cover generative AI for healthcare, its role in healthcare, and different applications of it. And we'll also discuss the challenges like model hallucination, which is related to generative AI. We'll also look into the use case, how Gen AI can be used for generating virtual staining techniques to speed up the pathology. We'll also explore agentic AI, explainable AI, as well as responsible AI. So by the end of this talk, you will have a clear understanding about the common practices, the current approaches, and the current research stand in the field of AI for healthcare. So starting with predictive analytics. What is predictive analytics? Basically, it is the evaluation of current and historical data through the statistical modeling, the data mining techniques, the artificial intelligence or machine learning and deep learning techniques can be used to predict the future events. These all techniques can be applied to structured data as well as unstructured data. If we talk about healthcare system, then the structured data is the electronic health records, and the unstructured data can be the clinical notes and imaging reports. The predictive analytics in healthcare can be used to predict the likelihood of a particular health condition, the clinical decisions, the trends, or even we can identify the spread of diseases. These are, of course, not limited to, but these are the five major use cases of predictive analytics in healthcare. One is the readmission prevention, the clinical decision support, then health insurance management, then population health management, and clinical research. So what is readmission prevention? Basically, nearly 1 in 5 adult patients, almost 18 to 19% in the United States, are readmitted to the hospital within 30 days of the discharge. These readmissions cost the healthcare systems of US over almost $52 billion annually, which is, and this figure is not stopping every year, it is increasing. The personalized predictive analytics enables healthcare providers to identify the patients at high risk of readmission, and then the hospitals can take preventive actions, can identify the different discharge protocols for different patients, can do the follow-up for reducing these readmissions. And these benefits in improving the patient outcome and safety. It lowers the unnecessary hospital spending. Almost 82% of US hospitals are penalized under HRRP, which is Hospital Readmission Reduction Program in the US. So 82% hospitals are penalized under this readmission program. So if we can use predictive analytics, if we use the data of the patient, and if we identify the probability of readmission of a particular patient, then necessary actions can be taken, and which can improve the performance and avoid costly financial penalties to the hospitals. Predictive analysis can be used for clinical decision support. We can identify the disease well in early stages, because if the disease is detected early in the stages, then the preventive actions can be taken. The patient can be survived, but many a times it is very difficult in case of traditional system to identify the disease in the early stage, and later on it becomes too late to survive the patient. We can identify, we can forecast a patient's response to specific treatments, and which minimize the need for trial and error approaches. We can monitor the critical conditions. We can analyze real-time patient data to spot early warnings and improve patient survival rates. The predictive analytics can also be used for health insurance management. This predictive analytics can accurately forecast a patient's healthcare utilization, such as hospital admission or surgeries, based on historic data and clinical variables. So while taking the insurance agencies can take the data of a particular person, the historical data of the particular person, that in history, how many times he was admitted, how many insurance claims he has made, what is the age of this person, what are the current diseases the person is having, and depending on that, these insurance agencies can determine the policy charges for particular patient. The cost prediction can also be estimated. Cost prediction can also be done. A patient's expected healthcare costs can be forecast by understanding their past utilization treatment needs. And one main thing, the fraud prevention. It is very prevalent in countries like India. The payers, the insurance agencies can analyze claims data and identify fraudulent behavior patterns to detect it early and prevent insurance abuse. The financial loss in a study, it was given that the financial loss in US for due to healthcare fraud accounts for 3 to 10% of the funds spent on healthcare, which is almost $300 billion. The predictive analytics can also be used for population health management. The governments may be able to detect the disease outbreaks early by using predictive analytics to identify the group with potential exposure. It can also be used for clinical research for drug discovery. The 90% of drugs fail in clinical trials. So if we use predictive analytics, then we can improve the patient selection. We can harness the genetic biomarker and the EHR data, right? Electronic health record can be used to identify the patients for a particular type of the trial, for identifying the particular identification of the drug also. The adaptive trial design can be done using predictive analytics, and we can identify the early risk, or we can identify the benefit from this trial using predictive analytics. Multiple industries are working in this field of AI for healthcare, because it is one of the fastest growing industry. The hospitals, the pharmaceutical companies, and research institutes are investing heavily. And the main reason is that AI helps improve accuracy, reduce costs, and address resource shortages. We are seeing strong interest in predictive analytics based diagnostics, the drug discovery, because they directly improve the patient care and outcomes. The Google DeepMind Health was launched, and this was developed, uh, the tool that predicts acute kidney injury 48 hours before it happens. The Antilake, which is a San Francisco-based startup, uses deep learning to analyze radiology scans. And this Antilake has shown reduction in diagnostic turnaround time by up to 60% in pilot studies. The IBM Watson for oncology is the evidence-based treatment recommendation, and it ranks the confidence scores. The Watson was trained on 20 million oncology records and could suggest the treatment options comparable to expert oncologists in many cases. The Lumiata is an AI-driven predictive analytics company which focuses on healthcare cost, the risk scoring, and personalized care pathways. So number of industries are uh, working into the field. They are investing. Each and every government, the government of each and every country is also investing huge amount of money for healthcare and for healthcare related research, and specifically the AI based healthcare research. There exists diversity of data if we talk about healthcare. The healthcare today is powered by a rich variety of data collected from many different sources, be it the lab test or proteometrics, the imaging, the phone or social media. The lab tests, which are the routine blood work, urine analysis, and which helps clinicians monitor the organ function, infection, and many more things. The proteomics analyzing the proteins present in the body. We gain molecular level insights that allow the disease mechanism exploration and the development of personalized treatments. The imaging, such as X rays, the MRIs, the CT scans, provide a window by which we can look inside the human body. The phones and wearable devices are transforming the care outside the hospital. These tools measure the steps, the sleep, the glucose level, and other health parameters, empowering patients and informing clinicians with actionable and real world data. The genomics is reshaping the medicine. Analysis of DNA and genetic markers enable us to assess the disease risk. The social media is increasingly recognized as a tool for understanding the public health trends and the patient sentiment. The group discussions and posts on social media, using these posts, we can determine the early outbreaks. We can identify a particular disease at particular location. So harnessing this multitude of data from lab to clinic to the phone and social sphere enables healthcare teams to provide more predictive, preventive, and personalized care for every patient. And predictive analytics, the AI, the deep learning can be used for all this purpose. So basically, this image shows that the predictive analytics imparts every part of healthcare, from managing data and designing research to direct care and communication with patients. Predictive tools help teams make better decisions, identify at-risk patients, improve the care coordination, and streamline billing and documentation. The IT, or for example, the IT operators benefit from automated data processing and maintaining the smooth data flow. The care managers coordinate care for high-need patients, helping reduce readmissions. The health analysts use dashboards to visualize patient outcomes and performance metrics. The patient engagement team send automated messages encouraging preventive checkups and treatment adherence. No matter the role, be it the IT or clinicians or managers or researchers, the predictive analytics provides valuable insights and support across the entire care process. So now let's dive into how. So one component of predictive analytics or one component of AI is the deep learning. So let's dive into that, how deep learning can be used in healthcare. So basically, deep learning models analyze the complex healthcare data, including medical images, electronic health record, the patient histories to aid in faster and more accurate diagnosis and treatment. There are a number of different applications where deep learning can be used for healthcare. One is the medical imaging and diagnostics, which detects the abnormalities in X-rays, MRIs, CT scans. Second is the early disease prediction. The deep learning model can forecast the disease progression, patient readmission risk, the treatment response for predictive care. It can be used for natural language processing, where you can imagine a thing, and many of you might have used it also. Let's say the ChatGPT or Perplexity, you might have uploaded your clinical report, your lab report to the model, and you may have asked LLM to explain it in a non-clinical way, to explain it in a very naive way so that I can understand what this report says, what the doctor says, what preventive measures I should take. So such kind of thing can be done. Personalized medicine, the tailored treatments using deep learning on genomics and lifestyle data for optimized patient outcomes. So out of all these different applications, we will focus into medical imaging, that how deep learning can be used for medical imaging in healthcare. So what is medical imaging? So basically it encompasses a variety of techniques used to create visual representations of the interior of the human body. Throughout our life, we have done number of different X-rays. Here you can see in the lower part of the slide, there is an image of the sonography. Another is the image of the brain, the MRI, the chest X-ray is there. Then the last image, the pink one, is the pathological image, which is the histopathology image, the whole slide image. which is used to identify the cancer tissues. So these are the different imaging modalities. We all know about it, but let us have a little bit knowledge about it. The X-ray, which is a radiography which uses ionizing radiation to visualize bones and certain soft tissues. Next is the CT, which is computed tomography, which produces detailed cross-sectional images combining multiple X-rays. Then is the MRI, the magnetic resonance imaging, which uses magnetic fields and radio waves to generate detailed images of soft tissues without radiation. The ultrasound employs high frequency sound waves to visualize real-time tissue movements and blood flow commonly used in obstetrics and cardiology. The whole slide image, which I have shown in the last slide, it digitizes the entire pathology slides at high resolution, creating virtual histopathology images. All these whole slide images are of size, one image is of size 1 GB. So it is similar to the size of the satellite images. We one image is of 1 GB. You can imagine the how high resolution images they are producing. And these images are used extensively for cancer assessment, be it the breast cancer or prostate cancer or lung cancer. What are the issues in traditional medical imaging? The one of the issue is time intensive analysis. The radiologists spend hours analyzing the complex scans. Second is the human error susceptibility. The subtle abnormalities can be missed in early disease stages. Let me tell you one real world scenario. There was one patient which was having a very small stone in the ureters. In as we went to the doctor and doctor suggested for sonography, we have done sonography, but the thing was detected in the sonography. But the patient was having the symptoms related to the stone. The stone means the pathri, which we call in normal life. So the symptoms were there, but in sonography, nothing was revealed. So the doctor suggested to do the CT. Then in CT, there was a very small white mark. And based on the symptoms, the doctor said that as the symptoms are related to the stone, this white mark may be a stone. The doctor was not confident, but later on it was a stone which was identified. So there exist very small abnormalities can be missed by the doctors, which can be identified by the deep learning model. The specialist shortage. This is very prevalent in India. The limited availability of expert radiologists, especially in rural areas. We know the condition of rural areas, and especially in Gujarat, the villages of Gujarat or the villages of Rajasthan does not have enough radiologists in the hospitals, and that's why they have tie-ups with the private radiologist. And what they do, they do all these different scans, then they come to the doctor. The doctor gives some analysis, doctor gives some reports, or doctor gives some conclusion, and they go back to their village. So this is the shortage. Specialist shortage is very prevalent in India, and here the deep learning can be helpful. Inconsistent interpretation, the variability between different specialists diagnosis. Ultimately, the doctor has to identify from the image which has been taken using microbiology or microscopic tools. Now there exist different interpretations among different doctors, and many a times that is why we usually take we usually call, let's take the second opinion, let's take the third opinion, right? And the another last challenge is the volume overload, increasing as there is a shortage of the specialist. And for the country like India, which has more than 100 CR population, this is really understandable that volume overload will be there for this radiologist, and it will be very difficult for them to complete everything in the stipulated time. And due to this overload, their analysis may be wrong. They may do the wrong analysis, right? So to overcome all these challenges, we can use deep learning. The deep learning can automatically extract features from complex medical images without manual programming. It can detect subtle patterns which are invisible to human eye. It can process multiple imaging modalities: X-rays, MRIs, CT scan, ultrasound. So if you if you show X-ray or CT scans to or ultrasound to radiologists, the radiologist will be able to read from them, right? But if you show histopathology images to radiologists, the radiologist will say, this is not my task. This will be analyzed by the pathologist. And if you give this MRI or CT scan to pathologist, he will say, I am not the person to understand these images. But we can train a deep learning model which can understand all these different varieties of images. This deep learning model can learn his hierarchical representations from pixel level to image level to slide level to whole slide level, right? And which makes their predictions much more better. So now let us dive into the different use cases of deep learning for different types of disease in the healthcare. So one of the very prevalent diseases is the lung cancer. Basically, lung cancer results in over 1.7 million deaths per year, which makes this disease the deadliest of all cancers worldwide. It is more than the breast cancer, prostate cancer, and colorectal cancer. It is the sixth most common cause of death globally, which is according to World Health Organization. Now, it is one of the worst survival rates among all cancers. However, if interventions are done, if this is identified in early stages, then it can be cured and the patient can be survived. But what happens that in majority of cases, these cancers are not caught in early stages. So there was a study, the state of the art study was conducted for lung cancer prediction from the medical images. The images are low dose CT images. The study was conducted by Google AI, the Stanford Healthcare, and New York University. What they have done, they have used a data set of LDCT, which is low dose CT. So basically, low dose CT is nothing but the CT scans, but with 30 to 40% less radiations. And they have used full volume 3D CT scans, almost 42,000 images, chest CT screening cases they have taken from NIH research data set, which has been collected from the National Lung Screening Trial Study as well as the Northwestern University. And they have validated these results with another well-known data set. Moreover, they have also compared the result against 6 US board certified radiologists. So the paper was published in 2019, which is end-to-end lung cancer screening with three-dimensional deep learning on low-dose chest computed tomography. So this was the idea. This is the block diagram of their approach. So basically, it contains three different models. You can see here, one is the full volume model, which is a deep learning model. Second is the cancer ROI detection, which is another deep learning model. And third, which has been shown in this pink box, which is another deep learning model, which is the cancer risk prediction model. So basically, this full volume model takes the current CT images, right? So basically this model is constructed by 3D convolution neural network, and which is designed to perform end-to-end analysis of entire CT scans. So basically what this model does, it takes these current, the present LDCT images as input and produces learned features as output. So it learns the complex spatial patterns across the whole scan and it produces the learned features as output. The second model is the cancer ROI detection. It is trained as for identifying the region of interest for the particular cancer, right? So it basically localizes the cancer tumors. This model focuses on identifying the candidate cancer region within the 3D CT volume. And to strengthen the training, the additional labeled bounding box marking of suspicious areas were done by the team of the researchers. And the third model, which is the cancer risk prediction model, this model takes the output of the previous two models, the output of the full volume model, which are the learned features, as well as the output of the cancer ROI detection model, which localizes the cancer tissues. And this model not only takes the current CT scans, but the previous CT scans of a particular patient, if any. And collecting all these, it this model produces the result. The results can be, one is the probability of the tissue, moreover is it also localize the cancer tissues. The result produced by this deep learning model was validated against 6 different uh, radiologists in the United States. So here, this diagram, you can see two different images, one on the left and second is on the right. So on the left, the yellow, the green, as well as the red marker are nothing but the average output of this radiologist. And on the right, you can see the output of 6 different specific output of this 6 different radiologists. On x-axis, there is it is 1 minus specificity, and the y-axis shows the sensitivity. So 1 minus specificity is nothing but the rate, false positive rate, and y-axis shows the true positive rate. The blue curve represents the performance of the deep learning model, and which is achieved the AUC, the area under the curve, of almost 96%, which indicates very high diagnostic accuracy. You can see various colored circles on the right hand side of the image, right? There are 6 circles for each color. One color is green, second is yellow, and third is red. What these 3 different colors are there? So basically, these 3 different colors are representing 3 different lung RADS criteria. Basically, lung RADS is nothing but a lung CT screening reporting and data system, which is a standardized framework for categorizing the lung nodules detected on LDCT scans based on size, appearance, and growth. And this lung RADS provides different types of thresholds in the range from 3, then 4A, 4B, 4X. So 3 means the tissue is probably benign. 4A means the tissue is suspicious. 4B means the tissue is very suspicious, and 4X means highly suspicious. So here the authors have used 3 different thresholds for the results of 6 different radiologists. One threshold, the green marked threshold, is the threshold 3 plus. So 3 plus means if any reader identifies, or so 3 plus is the means 3 and greater than 3 will be considered as positive, and likewise for other thresholds, right? So you can see that the output of all these 6 radiologists, all these 6 readers, for each of these 3 threshold is below the blue curve, which says that the model's true positive rates are much more than the true positive rates for any reader for any threshold for the given false positive rate. I hope you are understanding. But if you look at the right hand side of the path, you just pick one point on the x-axis, let's say 10, right? So on 10, if you see, the true positive rate of the model is 90, but the true positive rate for all other 6 radiologists is much lesser than 90. So this study reveals that the deep learning approach not only matches, but it can outperform the human experts in lung cancer detection. Another study is about diabetic retinopathy. Diabetic retinopathy is a serious microvascular complication of diabetes that damages the tiny blood vessels in the retina. The tiny blood vessels in the retina are nothing but the light sensitive tissues at the back of the eye. It stands as a leading cause of severe vision loss and blindness, particularly among working age adults. In the early stages, this diabetic retinopathy often presents no symptoms or only mild changes in the vision, which is why many people are unaware they have this condition. But as the disease progresses, the symptoms such as blurred vision, dark spots, and even vision loss can occur. The early detection is critically important because damage begins slightly and vision may remain normal until the condition advances significantly. So if this disease is detected in early stages, the vision of a patient can be survived, right? Can be saved. Now, To understand that how deep learning can be used for identifying the diabetic retinopathy, we need to understand that how in traditional way the ophthalmologist identify the diabetic retinopathy. So basically to diagnose it, the ophthalmologists begin with a thorough retinal examination. They use instruments like an ophthalmoscope or specialized fundus cameras to inspect the blood vessels and the macula. Macula is the central portion of the retina, right? So they look into the blood vessels and macula for the early signs, right, which indicates the abnormal new blood vessel growth. The severity of disease is then assessed by these doctors, which is usually they use the scale defined by ICDR, which is International Clinical Diabetic Retinopathy Scale. And however, the scoring considers the features like the presence and extent of diabetic macular edema and helps clinicians document and state the disease accurately. There are challenges in manual identification. The early indicators are often very subtle, as we have seen that it may be overlooked, especially when image quality is poor. Additionally, the sheer volume of images requiring to review puts immense strain on clinicians, increasing the risk of human error. That is the workload. Next is the intergrader variability, right? The inconsistency among different doctors, all these limitations which we have seen previously also for medical imaging, and the limited resources. There are shortage of trained specialists, especially in the rural areas. So here, a deep learning can be a survivor. So another study was from Google, the joint study between Google, University of Texas, California, as well as the 3 Indian hospitals. They have used the data set from IPEX in the United States, as well as the images were taken from 3 prominent Indian hospitals. One is Arvind Eye Hospital, the Sankara Netralaya, and the Narayana Netralaya. The paper was published, as you can see in the lower part as a footnote. The paper was published in 2016. The name of the paper is Development and Validation of Deep Learning Algorithm for Detection of Diabetic Retinopathy in Retinal Fundus Photographs. This is one of the state-of-the-art paper in this field. So the data set for training purpose was used from these 3 Indian hospitals as well as the IPEX. The validation data set was from IPEX samples. Of course, there is no overlap between the validation data set as well as the training data set. They also validated their model results with MESI.2 dataset, which is the public dataset from the French hospital. Grading of diabetic retinopathy severity was conducted according to, as I said, ICDR, that is International Clinical Diabetic Retinopathy Scale. And for that, they have used 54 ophthalmologists for performing grading of different images, which was there in the development set, that is the training set. All these 54 ophthalmologists were either licensed in the United States or were in the final year of ophthalmology residency. And each ophthalmologist graded between almost 20 to 60,000 images with median of 2021, and 10% of the derivation set, right? That is the total training set was 128,175 images. 10% of it was double read. The double checked, the grading was double checked by other pathologists also. The model which they had used was InceptionNet V3. And this is the much more detailed report of the data set which they use. So as I said, for training data set, 128,175 images were used and 54 ophthalmologists graded it. For validation, the IPEX 1 data set, they used almost 9,000 or 10,000 images, and they validated or they graded, they contacted 8 different ophthalmologists for grading of this validation set. Another validation set that they used was MESI.2. Total 1,748 images they used for this, and total 7 ophthalmologists graded this data set. Other details you can read later on. And these are the results. So on the left-hand side, the results of IPEX-1 has been shown. The validation data set IPEX-1 result has been shown for the deep learning model, the predictions of the deep learning model. And on the right hand side, the results related to Macedor-2 has been shown. In both of these cases, we can see the area under the curve, the AUC is almost 99%. And the square box is nothing but the zoomed version of this particular area, right? Once again, on x-axis, 1 minus specificity, that is the false positive rate, and on y-axis, the sensitivity has been shown, which is the true positive rate. The black curve is nothing but the model results. Each colored dot stands for the performance of individual human expert. As I said, 8 experts for IPEX were there and 7 for Macedor were there. And here we can see that the results of all these experts are very near to the results of the deep learning model. For IPEX, of course, the result of few ophthalmologists is slightly better than the deep learning model. However, for Macedor data set, most of the results of ophthalmologists were much lesser than the results of the deep learning model. So this says that this model achieves near perfect accuracy and performs comparably or even better than experienced human graders. Another study was related to skin cancer detection. The skin cancer is the abnormal growth of skin cells and is one of the most common type of cancer worldwide. And the three main types of skin cancers are basal cell carcinoma, the squamous cell carcinoma, and melanoma. The basal cell carcinoma is the most prevalent form. It often appears as a flesh-colored pearl-like bump or pinkish patch skin, which typically developing on areas exposed to sun, like the face and the neck. You can see the basal cell carcinoma, which is there in the image B. Another type of cancer is the squamous cell carcinoma is the second most common type. It usually manifests as red, scaly patch, firm bump, and or the open sore that doesn't heal well. It too frequently occurs on sun-exposed skin. Here, the image A is of the squamous cell carcinoma. And melanoma is the most serious form of skin cancer because it can spread quickly to other organs. So it often arises from changes in existing moles or appears as an irregularly shaped and multicolored dark spot. So you here the diagram F, you can see the malignant melanoma, right? It has white colored spots, then yellow colored spots, as well as the pink colored spots are there. The study says that there are almost 5.4 million new cases of skin cancer in United States every year. Although melanomas represents fewer than 5% of all skin cancers in United States, they account for approximately 75% of all skin cancer related deaths. So out of 100 deaths related to skin cancer, 75 cases are due to this melanomas carcinoma skin cancer. And that's why it is the deadliest skin cancer. And this it is approximately related to 10,000 deaths annually in the United States. So you can understand how important it is to identify this melanoma carcinoma skin cancer in early stages. Of course, the early detection is critical as the estimated 5-year survival rate for this melanoma drops from over 99% if detected in earlier stages to about 14% if detected in later stages. So if it is detected in earlier stages, the survival rate is almost 99%, the 5-year survival rate. However, if it is detected on later stages, the rate drops to almost 14%. So there are 14% chance that the person will survive. So a study was conducted how deep learning can be used for identification of skin cancer. The study was conducted by Stanford University. And for this study, they utilized a large and diverse data set for training the deep learning model as well as for validating the deep learning model. The data set comprised of 1,29,450 images covering sourced from 18 clinical curated repositories, open access online databases, and clinical data collected at Stanford University Medical Center. To build and train the model, the researchers has used Inception Net V3 model, and the paper was published in 2017. The title of the paper is Dermatologist Level Classification of Skin Cancer with Deep Neural Network. So the title itself says the deep neural network performs almost dermatologist level classification. So this is what the overall architecture or block diagram of the approach, that the data flows from starts from the left. You can see there is an image of skin lesion such as melanoma. This image is processed through the sequence of convolution, pooling, concatenation. So ultimately, this image passes through different layers of Inception V3 to extract increasingly complex and clinically relevant features. Of course, we all know that Inception V3, this model was initially pre-trained on the ImageNet dataset, which contains almost 1.28 million images across 1,000 general object categories. Later on, the authors have fine-tuned this Inception Net V3 model on the extensive dataset of 1,29,450 images. To structure the training, the authors have defined 757 different classes using a novel skin disease taxonomy. So here you can see the different 757 different types of classes the model will produce in the last layer. The probability score will be produced. However, for real world inference, in real world, we don't use all these 757 classes. So for real world inference, the model outputs clinically meaningful probabilities across the broader classes that map to actual diagnostic task. So for example, the model aggregates multiple melanoma subtypes, right? So melanoma has multiple subtypes. So each and every probability the model has given related to the melanoma are added, and then the final probability is given something like let's say there is a probability 92% malignant melanoma cancer is there. So this is how they have established the total ideology, and this image shows the output of the last hidden layer of the Inception Net V3 which they have trained. And this image shows four different skin disease. One is epidermal benign, epidermal malignant, melanoma benign, and melanoma malignant. The distribution of them, which was generated by the last hidden layer of the deep learning model, has been shown. This distribution is T-distributed SNE, which is the T-distribute stochastic neighbor embeddings. So basically, this TSNE is a method which reduces high dimensional data to two-dimensional for visualization purpose, which help us to understand how the model organizes information internally. So here, total 932 biopsy proven photographic test images are plotted. So each colored point corresponds to a single image, and the colors represent different disease categories. As it has been mentioned in the diagram, there are total 4 different colors for 4 different categories. So basically, this diagram tells us this plot reveals distinct clusters for each disease class and indicates that the CNN learns to group similar lesions closely together, right? And so basically, we understand that its learning is proper, right? You can see these orange colored cases are very near. Of course, there are a few false positives, there are a few blue points all there, but majority of orange colored points are near, the blue ones are near, the green ones are near, the yellow ones are near, right? So this demonstrates the model's ability to extract and encode clinically relevant features. Now this diagram shows the confusion matrix using heat map, right? So the one square, the first square is the confusion matrix for the deep learning model, and the 2 squares are the confusion matrix of 2 different dermatologists. On horizontal, on x-axis, there are predicted labels, and on y-axis, there are actual labels. And this metric or this evaluation was performed for 9 different categories. Those 9 different categories are shown below in the lower side or lower left side of the slide. From these, we can identify that. So basically, the dermatologist matrices are each computed using total 180 images from this 9 validation set. So 180 images were given from these 9 different classes were given to dermatologist 1, as well as those 180 were given to dermatologist 2. And for the deep learning model, this matrix is computed using a random sample of 684 images equally distributed among these 9 classes from the validation set. Now, the ideal thing is the darker there should be. Of course, the ideal case is there should not be any color in the area apart from this diagonal area, because this diagonal area represents the true predictions, right? Because in the diagonal area is that the predicted label of the model is 0 and the true label is also 0. The predicted label is 1, the true label is also 1. But here we can see there are errors for both of the dermatologists in identifying the class of the skin cancer, as well as there are errors in our deep learning model also. But we can understand that both CNN and the dermatologists noticeably confuse between benign. The major confusion exists in identifying the benign as well as the malignant melanoma lesions, which are the class 7 as well as the class 8. Just focus on class 7 and class 8, right? So row 7, column 7, row 8, column 8 for each of these three figures. You can understand that one thing you try to understand that uh, let's say, let's look at the dermatologist 1 result, right? So here, the true label 7, that is the benign melanoma, were misclassified into malignant melanoma. The same case was there for dermatologist 2 also. And the same case is there for the deep learning model. However, you can look at the color. The color of the deep learning model is much lighter than the two dermatologists, which shows that here in case of misclassification, the deep learning model performs better than these two dermatologists. But if you look at the other way, if the true label is 8, that is the true label is malignant melanoma, and either the dermatologist or the deep learning model has predicted benign melanoma, right? So here, if you look at the case, the row 8 and 7 column, there are 0 cases for dermatologist 1 and there are 0 cases for dermatologist 2. What it means that if the actual label is malignant melanoma and the dermatologist has identified it as benign melanoma, there are 0 cases, but there are few cases in case of deep learning. So here deep learning performs worse than this dermatologist. So this is how we can understand, we can evaluate the outcome, and we can compare the outcome of deep learning with two dermatologists. The another results they have generated using the validation, the whole validation set, and the model is tested against at least 21 dermatologists. So 21 dermatologists were used for identifying one type of carcinoma cancer and the melanoma recognition. And for each test, the previously unseen biopsy proven images of lesions are displayed to the dermatologist, and they were asked to make the prediction whether it is a cancer or not, or which type of cancer. The dermatologist outputs a single prediction per image, and it is represented by the single point in the diagram. So the diagram contains two images. One is A and B. Let us do not concentrate on B. Let us focus on A. So the red points which you can see are the results of the 21 dermatologists. On x-axis, there is sensitivity, not 1 minus specificity. The x-axis shows the sensitivity and the y-axis shows the specificity. The blue curve is for the model prediction. And here we can see that the results of all 21 dermatologists are much below than the results of the deep learning model, that says that the model is performing better than the dermatologist. So these were the lung cancer or the skin cancer or the diabetic retinopathy. All these examples tell that these deep learning models are performing almost at equal accuracy or near equal accuracy or slightly better accuracy than the certified dermatologist or radiologist or doctors. We know that how much years these doctors spend for their learning. They spend number of years for their learning, and we can train a deep learning model in within 1 week. Of course, the data collection task and validation task takes more days, but once the data is available, to train the model takes not more than 7 days or 14 days. So within 7 to 14 days, or if we complete the whole cycle of collecting the data, building the model, and validating the results, this whole cycle can be completed within a month. Within a month, we can make a deep learning model which can identify a particular disease, which can do a diagnosis with near human accuracy. So that is the power of deep learning model. Now let us look into the another dimension, generative AI in healthcare. So generative AI is booming nowadays, right? So let's see how generative AI can be used for healthcare applications. I need how much time is there? So Pooja ma'am, I'm just taking a pause here. Can you tell, am I audible clearly? Is my presentation visible properly?
Yes, sir.
Okay, okay. Thanks. Yes. So let's understand that how generative AI in healthcare can be used. So AI models that generate new content. So basically, what are generative models? So these generative models are nothing but the AI models that generate new content. The new content can be anything: the text, images, molecular structures, based on the learned patterns from vast data. These generative models enable synthesis of realistic medical data. Novel drug compounds can be found. Clinical notes can be automatically made, and education materials can be produced. These models combine multimodal data to improve diagnostics, treatment, and research. So, how generative AI can be used for healthcare applications? There are a number of different uh, use cases. One is synthetic medical imaging. We can generate realistic X-ray, MRI, and CT scan for training and diagnostic purpose. We can use these generated images for medical training and education, right? These images can also be used for the purpose of data augmentation for AI models, because these AI models for learning, they require huge amount of data, and many times in healthcare domain, getting a data is very difficult, and getting good data is also is another difficulty level, right? So if we can, from the limited amount of data, if we can generate real like data, so that our data set will become big, and we can do data augmentation, and we can train a deep learning model which can produce a good accuracy. Another use case can be these images can be used for simulation and for research also. It will help researchers simulate various scenarios or test different AI algorithms without waiting for new patient data. These images can be used for de-identification of data. The synthetic images that retain the key clinical features but do not belong to any actual patient. These Because in healthcare, the data privacy is the major concern, right? We give a number of different medical images to you, but those images should not reveal the identity of the patient. So generated such synthetic images does not have any relevance with the any physical person, right? This generative AI can be used for drug discovery and design also. It can accelerate new compound creation by simulating molecules. It can reduce the time and cost. We can design algorithms that can generate drug molecules, design trial protocols. It can predict outcomes during the clinical trials, right? The Google Cloud and Jingo BioWorks have collaborated to launch a new protein large language model and supporting API designed to transform the drug discovery process. This generative AI can also be used for clinical document automation. It can be used for personalized treatment plans. It can be used for claim pricing. Number of different use cases are there. But let us look into one of the use case, that how generative AI models can be used for generating uh, new medical images. And especially we will focus on how Gen AI can be used for generating whole slide images, which are majorly used by pathologists for identifying the tissues. So for pathology, so ultimately we are looking into AI-based staining of biological samples. So let us first of all understand what is staining and how this staining happens in the traditional way. Then we'll be able to, and what are the challenges in this traditional method. Then we'll be able to understand that how deep learning can be helpful. So for pathologists to identify the cancer and other disease based on biopsies, the nearly transparent sample of thin tissue sections must be stained with special dyes. It is a chemical process, right? And this is a well-defined method over a century in medicine. Now, the lab can take hours, sometimes up to days also, to stain a sample. AI algorithm could virtually stain a microscopic image in less than a minute, which will significantly speed up diagnosis of patients once the technology is ready for clinical use. Their results would be more consistent than the work of human experts, which can vary. The work of human expert can vary by country, by region, between different lab also, even among the work of a single technician also. So this image is showing the traditional way of histological staining. So the traditional way of staining is called histological staining, where we extract the tissue, we do fixation, embedding, sectioning, mounting, and then we do histological staining. This portion is very critical. It takes so much time, so much accuracy is needed here. And then these histologically stained slides are later on used for examination. Now, there is extensive research which is going on to generate virtual stains from histology stains using deep learning. So here in the diagram, let me little bit zoom. I hope you can see. Yes. So here in this diagram, the upper part of the diagram shows how deep learning can be used for generating label-free virtual staining. So basically, the label-free virtual staining is a process that begins with tissue extraction. Then standard preparation steps such as fixation, embedding, sectioning, mounting will happen. And then directly these images without any labeling. So label-free imaging will happen. Previously, we need to convert it into different dyes, and then we need to label them, and then we shall give it to the doctors for examination purpose. Here, after this stage, we will do label-free imaging. So ultimately, we will. So these are the physical copies. We need to convert them into a digital copy. This is the simple method. This is the simpler way of explanation, right? So label-free imaging is a thing, but converting these physical images into the digital one. And then those digital label-free images are given. So no labels are there, right? No different types of dyes are there. These images are given to the deep learning model, and this deep learning model is generating virtual histology image. So the stage of histologically generating this image previously, which was there in the traditional scenario, is ignored. And this also can be used in vivo imaging. This vivo imaging acquires images directly from the tissues within the body. So the images which has been taken using vivo images can also be given as raw input to the deep neural network model, which can generate virtual histological image. So virtual histological image is nothing but the image which has been generated by the deep learning model. And if we say histological image, that is the image which has been generated by the traditional model, because these two terminologies we are going to use in next few slides, right? So keep in mind. Now the lower part of this, which is labeled as stain to stain transformation. So basically, let me tell you, there are different types of stains. One is hematoxylin and eosin, that is H and E stain. Second is empty stain, which is Mason's trichrome. Third is PAS, that is periodic acid Skiff stain. Fourth is immunohistochemical stain, IHC. Another one is John Silver stain. These different types of stains are used for different purposes. And many a times for identifying a particular disease, the pathologists require uh, different stained images. for surety purpose, right? So in traditional environment also there is a requirement for converting image of one stain into another type, right? So can we use a deep learning model that if I have one image of one stain modality, let's say H and E stain image, can we use deep learning model to generate another type of stained images? So yes, it is possible and researchers are working on it. Researchers have made a good deep learning models mainly for these histopathological images. The major data set which is commonly used is this TCGA data set, that is the Cancer Genome Atlas data set, which includes a collection of more than 30,000 whole slide images for more than 9,000 cases. The other one is the Chameleon 16 and 17 data set, which are the famous data set. The other one is the prostate cancer data set, MyDoc data set. These are the different data sets which are used. Now I should go in little bit more speed. Okay, so let me explain you. The left hand side of this image is giving us the overall idea about how deep learning can be used for generating virtual stained images. Now there are two approaches. One is supervised approach and second is the unsupervised approach, right? So the A is the supervised approach. Let us focus on it. So basically unstained samples and the histologically generated slides are together will be used, of course, because the method is supervised though, so we must have ground truth with us. So both of these images will be so these unstained samples will be given for label free imaging, which will generate these label free images, and these histologically stained images will be given for bright field imaging, which will capture the colors and these things. So though these images are histologically stained images, which are we call HS images. Now next we need to do pairing of these images. We need to do image registration of these images. So we must match pixel by pixel. There must be a match between pixel by pixel between these two images, because these paired images are ultimately used to train the model. Then we need to do cropping and pixel level registration, as I said, and then these images can be used to train the model. So this is a supervised approach. In case of unsupervised approach, of course, we need these two samples, unstained samples also, as well as the histologically stained sample also. But this part will be removed. The image registration or the pairing of unstained image as well as the histologically stained image, because in supervised we need pair, right? So if this is the input, the corresponding output is this. But here unpaired inputs will be given as input to the model, right? So basically we tell the model that this is the distribution of the input and this is the distribution of the output. So based on this input, you should correspondingly generate output something like this. And once the model is trained, be it the supervised approach or unsupervised approach, later on for inference, it can be used like this. We will have unstained samples, which will be converted into a digital image, which is a grayscale image only. And this label free image will be given as input to the model. And later on, the model will generate virtually histological images. The right hand side of this figure is showing me the diagram that how deep learning, be it supervised or unsupervised, can be used for stain to stain transformation. So let us imagine that we have images of one stain type, let's say the stain type A, and we want to generate images of stain type B. So first of all, what we need to do, we must have these pairs of images, stain type A and stain type B. We must do pairing in case of supervised, and then those paired images of stain type A as well as stain type B should be given as input to the model. In case of unsupervised approach, pairing is not required. Unpaired images will be given as input to the model. Usually for this unsupervised approach, cycle gain is usually used, cycle gain deep learning model. And once the model has been trained, the blind inference stage. So if you give histologically stained type image A as input, the model will generate other stain type as the output. So this is what this whole slide tells. Let's move on to the next. So now once the model has been trained, how to evaluate the performance of the model? So there are different approaches different researchers have used. So one very simple approach is that once the image has been generated by the deep learning model, we have, let's say, one image is virtually stained image which has been generated by the model. We will compare that image with the actual ground truth which is available to us. And we'll compare both of these images. And there are a number of different evaluation metrics available to us. One is structural similarity and index measure, which is SSIM. We may calculate the mean square error or root mean square error. We can calculate PSNR, that is signal to noise ratio, peak signal to noise ratio. And depending on that, we can evaluate the model performance. Another one is the algorithm based quantitative feature analysis. We extract features from the model generated images, as well as we generate features, capture features from the actual ground truth images, and then we compare. The option C is widely used because we will compare these model generated images using human, right? So we use pathologist for diagnostic purpose. So what we'll do, we'll give a deep learning based generated image to the pathologist, and we'll ask them to identify whether there is a tissue or not, or do analysis on this image. And as well as we'll give the histopathological, the ground truth image to the pathologist. And based on the outcome of the pathologist, we compare, right? And another task can be, we can use both of these images for downstream task. Let's say the downstream task is to identify the breast cancer tissue. So one is to classify whether the breast cancer is there or not, as well as the second task is to localize the breast cancer, right? So what we can do, we can give deep learning generated images to the model, and we can calculate the RMSE score, or for classification purpose, we can calculate uh, the loss, the what we say, the classification loss, let's call. I am not recalling it. And we'll also give the ground truth images to the model, and we'll calculate the classification loss, and we'll compare both of the loss so that we understand that how results are, whether the results are near or different. So these are the different approaches for evaluating the model performance. So one of the study was conducted in 2019 by Revenson for generating virtual histological staining from biological samples, right? So he has designed a deep learning model. So what he has done, he has captured autofluorescence images, which are the label-free images. It has passed to the deep neural network, and it has generated the particular stained images from the deep learning model. And you can see in the diagram, the upper diagram is the actual ground truth image which has been generated by histological staining, and the lower diagram is nothing but the virtual stain images. So basically, this research has generated three different type of stain images. One is HND, second is John virtual stain images, and third is the empty stain images. And for generating each of these images, he has trained different uh, neural network models, different deep learning model. So the input for generating each of these three different stain type was the autofluorescence image. And here you can see on the right hand side, the leftmost part, the left image is the network output. The deep learning model has generated the deep learning model generated images, and the right path is the ground truth images. And you can see the similarity between these two type of images. And for validating it with human pathologist, what they have done, they have blinded to the staining techniques for each WSA, and each pathologist were asked. They have given it to, I think, three different board certified pathologists, and they asked the pathologist to grade each of these images in the scale of 4. So scale 1 means unacceptable, 2 means acceptable, 3 means very good, and 4 means perfect. The results reveal that the average score of all three pathologies for VS images, that is deep learning generated images, are either equal or more than the average score for HS images. HS images are the ground truth images or histologically generated images. Another study was conducted for stain transformation. As we have seen, we can use a deep learning model for transforming one stain image, that let's say H and E, to another type of stain image, that is PAS, right? So basically, multiple modality of stains are used for giving surety to the pathologist about the presence or absence of a particular disease. For example, non-neoplastic kidney disease in practice requires H&E stains are the first stains which will be captured by the pathologist. And pathologists often provide a preliminary diagnosis from this H&E image to start the treatment. And the final diagnosis comes later once the other stains like John's or MT stains are available, and which are available 2 to 3 days after, right? So can we use deep learning for generating or for transforming images of one stain to the other type of stains? So the study was conducted by D. Han Zheng and the team members, as well as the Rivenson, which was the author of the previous study. They have published a paper in 2021. The title was Deep Learning Based Transformation of H and E stains tissues into Spatial Stains. So what they have done, the input to the network, input to the model was H and E stains, and they have generated three different stains from the deep learning model. One was John's stain, second was the MT stain, and third was the PS stain. And they have compared the result with the pathologist. So for validation of the model, what they have done, they have used innovative approach, different approach. What they have done, they have identified three pathologists, board certified pathologists. Initially, they have given only actual H&E images, and they have asked to do the prediction. Later on, after 3 weeks, the phase 2 started. And in phase 2, they have given H&E image and virtual stain transformed images. So, the H&E image and other three stain images, which has been generated by the deep learning model, they have given it to the three pathologists. After 3 weeks in phase 3, they have given H&E image and histochemical stains of the other three, which has been given to the pathologist. And they have compared the result. On the left-hand side, the comparison is there. The upper square gives us the results of the phase 2, and the lower is giving us the results of case 3 in comparison of the phase 1. So they have revealed that they have done for first comparison, they have used 58 different cases, and they have identified that when they have given the deep learning based other stain images in addition to H&E based images, there was improvement in the outcome. Out of total 58, the 13 outcome were improved. There were 38 cases which was in concordant, it was in agreement with the initial H&D diagnosis, and there were 7 cases which were the conflicting results. If you look at the lower diagram, then the H&E image, the phase 1 is compared with phase 3, where in phase 3 we are giving actual ground truth images of other three stain types. And here the improvement was there in 15 cases out of 58. There was agreement in 39 cases, and there was disagreement in 4 cases. So this study tells that these deep learning models are also able to transform one type of stain into another type of stain. There was another interesting study, AI watching AI. This is a post recently you can find on the net, and this paper is published recently in 2025. AI watching AI, the dangerous errors in digital pathology caught by UCLA system. So basically, we all know that these generative models hallucinate, and this hallucination also happens with generating images, histopathological images. And there are mainly two types of hallucination. One is technical, which are unrealistic hallucination. So which are the hallucinations like blurred areas or folded tissues, something like this. And this type of hallucination are normally spotted by experts, right? And if it is spotted, then there are no issues. But the other type of hallucination are realistic hallucination. So what happens here? The replacement of some tissue components with imaginary ones. So maybe in the original image, in one particular region, there are no tissues, but the GenAI model has generated tissues. And these or in the other way around, that the original image contain tissues, but the generated model does not show any tissues, right? So these this might mislead the pathologist, and the results can be worse. So what they have done, they have used deep learning model to identify whether the deep learning model hallucinate or not. So basically, this is the approach which they have used. Will not go much into the detail of it. The approach is they call it autonomous quality assessment network. So what they have done, they are using virtually stained image, that is VS image, and another type of image is autofluorescence image, are the images which are usually given as input to the model, right? So ultimately, the task is to generate uh, virtual stain images from the autofluorescence images, right? And they have two different deep learning models. One model is generating uh, virtual stain image from autofluorescence images, and another deep learning model is doing the reverse thing. So what they have done, they are feeding a sequence of these images to the deep learning model. Here, the blue ones is nothing but the ResNet backbone which they have used, and then they are generating the final scoring. If your final scoring of a particular image is greater than some threshold, it means the image is not containing any hallucinations. And if that score is below the threshold, then the image is unacceptable, cannot be used for further purpose. So what they have done, they have used input sequence generation, which is generated by the GAN, right? So the process starts with initial label-free or autofluorescence images, then virtual stain images getting generated. Then from virtual stain image, another autofluorescence image is generated. Then again, virtual stain images are generated, and these are passed as sequence to the model. So basically, the purpose of these cycles is the iterations amplify the subtle inconsistency or hallucinations. If the virtual stain deep learning model introduces errors, they accumulate and become detectable over the cycles as back and forth transformations highlight the deviations from physical consistency. This paper was recently published in 2025, and it will be become popular in within very short time. So these are the challenges in generative AI healthcare. One, the major challenge is model hallucination, clinical validation, regulation transparency, bias mitigation. Ongoing research is done to safely explainability and model integration. And the expected market will grow from 3.3 billion in 2025 to nearly 40 billion in 2035 within 10 years. I think 10 minutes left. I need to complete in 5 to 7 minutes. Just let's go quickly. Agentic AI revolution. So the future of this is the agentic AI. So what is agentic AI and how it will be used in the healthcare system? Let us try to understand. So basically, the agentic AI represents the evolutionary leap beyond the traditional predictive assistive system. And the key characteristics of healthcare related agentic AI can be: one is the goal oriented behavior. So autonomous pursuit of patient care objectives. Second is the proactive decision making, contextual adaptation, multi agent collaboration. So basically, we can understand the difference between traditional AI system. The traditional AI system is purely simply the deep learning based system. No agents are involved. So the traditional AI system rely on clear input and produce the output, whereas the agentic AI is goal driven, meaning they can identify the problem, they generate the solution, they make the decision, then they act with very minimal human intervention. The traditional AI help a doctor to identify the pattern in the lab results, whereas the agentic AI could identify the pattern, predict the future risk, suggest the treatment, schedule the follow-up, and keep the care team informed all independently. So it's like giving healthcare providers a proactive digital teammate that can think ahead, learn the job, and respond to changes in real time. So this is the future of healthcare system. This agentic AI can be used in multiple different approaches. So at present, From 2023 to 2025, we are actually in the era of traditional AI. From 2025 to almost into the 2028, the era of agentic AI research related to that will be done. And after 2028, we can imagine the autonomous AI, which will be active, right? Automatically, everything will be done. Now, the very important question, why should I trust you? We have trust issues amongst human also. Then how we can trust the output generated by the deep learning model? Because here we are using this deep learning model for healthcare system. If my deep learning model is generating wrong outcomes, there are very serious repercussions of it. So explainable AI, the explainable AI actually tells that this is the output of deep learning model, but how this deep learning model has reached to providing this outcome. So we have to go from black box machine learning to white box machine learning. We understand, many people says that these deep learning models are a black box, right? We give some input, it gives some output, but for healthcare systems, this answer is not acceptable, right? So if let's imagine you are the designer of the deep learning model, and you have been given the task to identify the whether the person has cancer or not, or what is the survival rate of the person, right? And if your model misclassifies, right, the hospital can't say that the model was designed by some X person. You should ask to them, no, they must be responsible, the responsibility must be fixed, right? I wanted to explain this famous husky versus wolf classification related to explainable AI, but we can skip it. So why it is important in healthcare? Because healthcare deals with life and death decisions. There should be legal accountability, should be fixed. Regulatory compliances are there, which must be followed, and we must earn the trust not only in patient, but we must earn the trust from the clinicians, from the doctors, from the hospitals. So basically, explainable AI, it helps in clinical decision support enhancement. It validates AI recommendations against the clinical knowledge. It identifies the potential biases. It educates the patients about the diagnosis. With clear reasoning, it ensures accountability when AI-assisted decisions lead to adverse outcomes. And these are the common approaches to explainable AI. The SHAPE, LIME are the famous models, the grade game, attention mechanisms. There are challenges in implementing explainable AI. There are trade-offs like complexity versus interpretability, the model dependency, we may skip it. And as we proceed, there is, of course, we know this AI can be used for good, it can be used for bad also, but for even in for the good cases also, the AI must be responsible. So nowadays, in addition to explainable AI, the responsible AI is booming. Responsible AI and ethical consideration. And when we are dealing with healthcare system, the responsible AI is much required. So what this responsible AI is ultimately telling, that one is the fairness, that equal AI performance should be there across diverse populations, across different races, across different ages. There should be transparency, a clear AI decision rational, which should be accessible to clinicians, to patients also. Accountability must be defined. The privacy, the secure data handling, and patient consent must be taken. Safety, rigorous validation, and continuous monitoring should happen. The equity and bias, the algorithm trained primarily on data from certain demographic groups may perform poorly for totally different demographic population, which leads to unequal healthcare outcomes. Basically, this diagram shows what's needed to make AI system healthcare both trustworthy and effective. To be reliable, these tools must have strong data quality, safeguard privacy. These systems should work well with clinicians and offer clear and explainable results. They also need to be rigorously validated, clinically relevant, user-friendly, and fully compliant with ethical and legal standards. If you have designed healthcare based solutions, then you must pass through number of different legal standards, then and then your product will be used. These principles highlight some of the today's biggest open challenges and guide the future research, improving how and why AI makes decisions, reducing the bias by diversifying the data, keeping up with the challenging regulations, and finding better ways for AI to collaborate seamlessly with humans in real clinical settings. The ongoing goal is to ensure AI not only performs accurately but also earns clinicians as well as the patient's trust while delivering real world health benefits. So, to conclude, from predictive analytics that forecast disease risk and optimize the resource allocation to deep learning breakthrough we have seen in medical imaging like detecting lung cancer, diabetic retinopathy, skin cancer, which has achieved near human accuracy. We have seen how AI is transforming diagnostics and patient outcomes. We have explored generative AI's role in creating synthetic data for training, drug discovery, the histopathological image generating. We have also, but of course, we need to remember that the great power comes with great responsibility. Explainable AI is required. The black box must be opened, it must be converted into the white box, and the responsibility, the ensure of the fairness, transparency, and equity should be across the diverse population. Looking ahead, the fusion of these technologies with ethical framework will usher in the era of proactive, personalized healthcare that saves lives and reduces disparities. As the researchers and practitioners, it's our duty to innovate responsibly and collaborate to make this vision a reality. So thank you for patience listening. I hope I have completed in time. I hope I did not make you bored. Shall I stop
Sir.
my presentation?
Thank you, sir.
If
Thank you very
there
much,
are
sir.
any questions, I'll be
Yes.
happy to answer them.
Any questions from the participants? Okay. Oh, thank you, sir. Thank you very much, sir, uh, for your informative session. And it was a really a nice session, very informative session. And also, I am very thankful for supporting me for this FDP. Whenever I require your help, you are already, you always replied me. Thank you very much, sir. Thank you.
Most welcome, ma'am. Most welcome.
Thank you, sir.
So once again, thank you to Pooja ma'am for inviting me for this excellent FDP. And I wish that all participants will gain much knowledge, will gain information in the field of this healthcare based AI and from the other experts which are coming. Thank you.
Thank, thank you. Thank you, sir. You may leave us.
Yes, ma'am. Yes, ma'am.
So